In this recording, we're going to talk about logistic models, which are really population models. And population models that have scarce resources and ultimately do not grow forever. And so here's a differential equation for a logistic model. The rate that the population changes here on the left is proportional to the product of the population and some other criteria about the environment. And so as we look at each one of these factors, these are two things that are multiplied by each other. If either factor is equal to 0, the slope or the rate of growth will be 0. And so that means that there's going to be 0 slope according to the slope field along the x-axis, because population will be the y-axis, and this of course will be time. Also, when 2 minus p over 10 is equal to 0, or when 2 equals p over 10, or when p equals 20, we will also have 0 growth rate. So we could also draw horizontal slopes here. Now let's take a look at when time equals 0. Time equals 0, we'll have some amount of population, and we don't really know from what's given here because notice t never shows up in this logistic model anywhere. But in a word problem, you would be given some initial population. And from there, as you can see with our slope, the more the population is, let's say that up here we've got a population of 20. And that's because we have a horizontal slope. We are going to grow and grow and grow and grow, but then level off as we near what's called the carrying capacity. So our carrying capacity will always be that upper horizontal asymptote. And there will be a lower horizontal asymptote. Typically, that will be at population equals 0. And that shows up in this case. Population 0 and population 20 were our lowest we could ever get. So if we were going to ever continue off to the left, the limit as time approached negative infinity of our population would be 0, and the limit as time approached positive infinity of our population would be 20. There's a couple other ways that this same logistic differential equation could be written. You could write dp dt equals p times 20 minus p all over 10, and the rate the population changes, dp dt, equals p over 10 times 20 minus p. But in all cases, setting each of the factors equal to 0 will represent in your horizontal asymptotes because there is 0 slope. The last key thing that you're likely to be asked is at what location or at what time, or more likely at what population, because time will be hard to know just from the differential equation, but you might be asked, what population is the population growing the fastest? All that means is, when is its rate of change the fastest, or when is its slope the fastest? And hopefully as we look at the graph here, you can see that we are steepest right here on the graph, and that turns out that that will always be the carrying capacity divided by 2. As long as the carrying capacity and 0 are the asymptotes. So we would really have 20 plus 0 over 2. That's our population of fastest growth. Here's a new model for growth for a wolf population, wolves in a sanctuary. So as we look at this, let's say we're asked, what's the carrying capacity of the population? Well, I would look at each factor. We want our slope to be 0. So if p minus 2 is equal to 0, then p equals 2. And if 30 minus p over 2 equals 0, then 60 equals p. And so 60 then will be our carrying capacity. A little sketch would suggest that we're going to have 0 slope up here at population of 60. Interestingly, though, in this case, our minimum population looks like it's going to be 2. And so maybe there would be a breeding pair, and we would make sure that there was never any less than 2 in the population by making sure that that alpha male and alpha female were healthy. That means our graph will look something like this. And that means the limit as t approaches negative infinity, well, that would be our lower horizontal asymptote of 2 wolves. No matter what happened, we would make sure that there was never a smaller population than that. And then how many wolves are present when the population grows the fastest? Well, we're going to be at this midway point again. That's where our slope is the greatest. That midway point will be halfway between 60 and 2, or the average of 62, which is 31. So at 31 wolves, that's when we grow the fastest. What if you were asked to sketch a solution curve for 2, 70 on that same differential equation and explain the meaning? Now, we don't have all of the slopes, so we're just going to ballpark where that would be. If this is 60 here, then let's say 2 on the x-axis might be there, so 270 might be right here. What would happen is that our slope field also is approaching 0 as t goes to infinity, and so our solution curve might look something like what's shown here. And the meaning would be that more wolves than the population or the environment can handle start, and over time, wolves die out to meet the carrying capacity.